Welcome. I am Dr. V.Sulochana, Assistant Professor of Mathematics, Seethalakshmi Ramaswamy College, Trichy. In this video, we are going to see graph labeling using the concept of number theory. First, we shall see the introduction from graph theory. Next, we see the construction of graphs, and then we see the number theory concepts. And finally, we shall see the application of number theory concepts in graph labeling. Graph. A linear graph, or simply a graph G equal to V, E, consists of a set of objects V equal to V1, V2, etc. called vertices, and another set E equal to E1, E2, etc. whose elements are called edges, such that each edge EK is identified with an unordered pair Vi, Vj of vertices. The vertices Vi, Vj associated with edge Ek are called the n vertices of Ek. Graph labeling. A graph labeling is an assignment of integers to the vertices or edges or both, subject to certain conditions. If the domain of the mapping is a set of vertices, then the labeling is said to be a vertex labeling, and if the domain is a set of edges, then the labeling is said to be an edge labeling. Next, we shall see the definition for edge-graceful labeling. A graph G of V, E is said to be edge-graceful if there exists a bijection F from the set of edges E to the set 1, 2, etc. Q, such that the induced mapping F plus from V2 to the set 0, 1, 2, etc. P minus 1 given by F plus of X is equal to summation F of XY mod P taken over all edges XY is a bijection. In short, we say that edges should be labeled from 1, 2, etc. Q, and then the vertices will receive the labels from the set 0, 1, 2, etc. P minus 1 by the condition that sum of all edge labels incident with the vertex and taken mod P. Now we shall see the illustration. Consider the graph in the figure. So in this graph, we have 4 edges and 5 vertices. Hence the number of vertices P equal to 5 and edges Q is equal to 4. Edges are labeled from 1, 2, 3, 4. So I am labeling the edges as 2, 1, 3, 4. So when we consider the vertex labels, the vertex label should be from the set 0, 1, 2, 3, 4. Now consider this vertex. So this vertex should be labeled by adding all the edge labels incident with that vertex, and we shall take the modulus of the 5 value. So 2 plus 1 plus 3 plus 4 mod 5, that is 10 mod 5. So 10 mod 5 value is 0. So 0 is assigned to this vertex. Similarly, when we take the modulus of all the edge labels incident with the vertices, we get the labels as 2, 1, 3, 4. Now we shall see the construction of graphs. Let Gi I equal to 1, 2, etc. be the collection of disconnected graphs of same family. We now construct a connected graph G by adjoining a vertex L of each Gi satisfying a special property by the following steps. Step 1, set I equal to 1 and the graph H1 equal to Gi. Step 2, set the graph H2 equal to Gi plus 1. Step 3, set L be the vertex of H2 satisfying a special property. Step 4, adjoin L with any vertex of H1. Let the new graph be Gi dash. Step 5, set H1 equal to Gi dash. Step 6, set I equal to I plus 1. Step 7, repeat steps 2 to 6 until the values of I are exhausted. The graph obtained from the above steps be denoted by G, which will be a connected graph. We now explain the above definition with an example. Let G1 equal to P3, that is a path graph on 3 vertices, and G2 be P5, path graph on 5 vertices, and G3 be equal to P3 as in the figure 9.1 to figure 9.3. Let L denote the middle vertex of the paths. Now we are going to adjoin the middle vertex with the previous graph. Step 1, let I is equal to 1. The graph H1 equal to G1 equal to P3. Step 2, the graph H2 equal to G2 equal to P5. Step 3, L be the middle vertex of H2. Step 4, adjoin L of figure 9.2 with any of the vertex of H1 and the new graph be G1 dash. Now I am going to adjoin this middle vertex to any of these vertices of the first graph H1. Let us see the illustration. Case 1, adjoin L of figure 9.3 with vertex V11 of figure 9.1. Then the graph G1 dash will be given as here. Case 2, when we adjoin L of figure 9.3 with vertex V12 of figure 9.1, then the graph G1 dash is like the following figure. Case 3, adjoin L of figure 9.3 with V13 of figure 9.1, then the graph G1 dash is given here. So we have all the three cases here. Next, step 5, set H1 equal to G1 dash. Step 6, I equal to 2. Step 7, H2 equal to G3 equal to P3 and L be the middle vertex of H2. So we are considering the third graph. So when we consider the third graph, the path graph P3, and we adjoin any vertex of the path graph P3 with any vertex of the previous graphs obtained, we have the following cases. So this is a case 1 when we adjoin the vertex of the path graph P3 with the first vertex of the previous obtained graph, and these are the second case, and these are the remaining cases we have. So in each case, we have 7 graphs and we have 3 cases. Hence, we have constructed 21 graphs from 3, which includes symmetric graphs. Now, we are going to the concepts of number theory. Let us consider the Diophantine equation of the form x plus y equal to n. Here we are interested only for the case when n is odd. Let the solution set of the above equation be denoted by S. So S is equal to set of all ordered pairs xi, yi such that xi less than yi and xi plus yi is equal to n. Since n is odd, it is clear that either xi is odd and yi is even or vice versa. Let us see the illustration. Here is an example that helps us to understand the definition of D cycle number of n, D sequence cycle number of n, which will be discussed in the forthcoming slides. Consider the Diophantine equation of the form x plus y equal to 17. Then the solution set S is given by set of all ordered pairs xi, yi such that xi less than yi and xi plus yi equal to 17. So for x plus y equal to 17, we have S is equal to the set of all ordered pairs 1, 16, 2, 15, 3, 14, 4, 13, 5, 12, 6, 11, 7, 10 and 8, 9. I am going to consider one of the ordered pairs in the solution set and I am going to partition this set S with some criteria. Consider the ordered pair 1, 16. Take the even number in the ordered pair divided by 2. So we have the value 8. So the ordered pair which has the value 8 in the first value is 8, 9. So I am considering that ordered pair 8, 9. Now in this pair 8 is the even number and divided by 2. So that value will be 8 by 2 will be 4. So the ordered pair which has the value 4 is 4, 13. So when we divide this value 4 by 2 means we get the value 2. So the ordered pair with the value 2 is 2, 15. So once again when we divide 2 by 2 we get the value 1. So the ordered pair is 1, 16. So we have obtained an cycle. So this cycle is named as D cycle and denote this D cycle as Dn1. Then consider another ordered pair 7, 10. Here 10 is the even number. So divided by 2 we have the value 5. So 5, 12 is the next ordered pair. Next here 12 is the even value. So divided by 2. So we have the value 6. So 6 is in the ordered pair 6, 11. Here 6 is the even number divided by 2. So we have the value 3. So the ordered pair which has the value 3 is 3, 14. So we have extracted all the solutions in the solution set. Yes, sir. So this is the second cycle Dn2. So for this Diophantine equation x plus y equal to 17, n is equal to 17. For n is equal to 17, we have two D cycles D1 and Dn1 and Dn2. So the partition, we have the partition S into two subsets Dn1 and Dn2. Thus the D cycle number are given by the following definition. Let n be an odd number. S is equal to set of all xi, yi such that xi less than yi and xi plus yi equal to n be the solution set of the Diophantine equation. Then clearly either xi or yi is even as n is odd. From S, choose a pair say T1, T2. If T1 is even, then choose the pair T1 divided by 2, n minus T1 by 2. If T1 is odd, then choose the pair T2 by 2, n minus T2 by 2. If T1 by 2 is even, then choose the pair T1 by 4, n minus T1 by 4. If T1 by 2 is odd, choose n minus T1 by 2 divided by 2, n minus T1 by 2 divided by 2. Again, if T2 divided by 2 is even, then choose the pair T2 by 4, n minus T2 by 4. If T2 by 2 is odd, choose n minus T2 by 2 divided by 2, n minus T2 by 2 by 2. Repeat this process until we get either T2, T1 or T1, T2 with which we started. The process of arriving at the pair with which we started is called the D cycle. The number of partition of S into D cycles is called the D cycle number of N, denoted by dc of N. Let D and I for 1 less than or equal to I less than or equal to dc of N be the partition of N. Then the number of elements in each D cycle D and I is called the D sequence cycle number of N. Then for the previous example, we have DC of 17 equal to 2, cardinality of dn1 equal to 4, which is denoted by n1, and cardinality of dn2 equal to 4, which is denoted by n2. Therefore, n1 less than or equal to n2 is a D sequence of 17. Next, I'll see one more example. So n is equal to 15. For n is equal to 15, the solution set is given by S is equal to set of all ordered pairs 1, 14, 2, 13, 3, 12, 4, 11, 5, 10, 6, 9, 7, 8. Here dn1 equal to 5, 10, dn2 equal to 6, 9, 3, 12, dn3 equal to 7, 8, 4, 11, 2, 13, 1, 14. Here DC of 15 equal to 3, since we have 3 D cycles and the first set has the cardinality 1. So cardinality of dn1 equal to 1, which is denoted by n1, and cardinality of dn2 equal to 2, which is denoted by n2, and cardinality of dn3 equal to 4, which is denoted by n3. The set this n1 less than or equal to n2 less than or equal to n3 is a D sequence of 15. Now we are going to apply this number theory technique in graph labeling. That is, we are going to obtain the edge graceful labeling using this concept. So we are going to construct edge graceful graphs from D cycle, constructing edge graceful graphs from the Diophantine equation. So the points to remember are, here we give labeling for disconnected graph, which will merge into connected graph. Hence, n denotes the total number of vertices in the graphs. Illustration, for n equal to 15, the D cycles are dn1 equal to d1 equal to 5, 10, dn2 equal to d2 equal to 6, 9, 3, 12, dn3 equal to d3 equal to 7, 8, 4, 11, 2, 13, and 1, 14. Now consider the D sequence n1 less than or equal to n2 less than or equal to n3, which is equal to 1 less than or equal to 2 less than or equal to 4. So here we are going to consider the path P2ni plus 1. Consider the path P2n1 plus 1, which is equal to P3. Since for n1 we are having the value 1, so 2 into 1 means 2, 2 plus 1 is 3. So we are having the path graph on 3 vertices. So for dn1, d1 is equal to 5, 10. So assign the labels 5, 10 to the edges 5, 10. Then we have the vertex labels as 5, 0, 10. Similarly, dn2 equal to d2 equal to 6, 9, 3, 12. Consider the path P2n2 plus 1 equal to P5. Since n2 is equal to 2, 2 into 2, 4, 4 plus 1 is 5. So we have P5 path graph on 5 vertices. So we have the solution set value as 6, 9 and 3, 12. So give the edge labels 6 and 9 to the adjacent edges incident with the vertex having the label 0. Next we have the values 3, 12 for the remaining edges. So consider the path P2n3 plus 1, which is equal to P9 corresponding to dn3, d3 equal to 7, 8, 4, 11, 2, 13, 1, 14. We consider the path graph P9 and we label the edges from the solution set. Then we have the edge graceful labeling. Now we are going to merge these graphs by fusing W1 of G1 with any vertex of G2. We arrive at 5 family of graphs, say G4. Again, by fusing this vertex W3 of G3 with any of the vertices of G4, we arrive at the 7 family of edge graceful graphs. Now I am going to give one of the fusing form. So this is the fused graph. Similarly, we can obtain the remaining graphs. Thank you.